These will be the notes for one of our last sections. We're going to do a big topic in a field of study called differential equations, and we're going to be solving them by a process called separation of variables. But before we even begin, let's discuss what a differential equation is. When you're given what's called a differential equation, it means you're given an equation for the derivative or for the rate of change of something. And when we solve a differential equation, we want to figure out what the original function was. So in terms of dy dx, that's kind of what it means to solve a differential function. However, in real life, our variable of change is predominantly time, and so it's usually something dt, and it's usually something that's increasing or decreasing over time. A lot of times it'll be like bacteria or population, or for Newton's law of cooling, it's the temperature of something going down. But on the top is usually, I'm just going to put b for maybe it's bacteria, and what you're given is the rate of change, like how fast the bacteria is growing, or maybe even how fast we're killing it off. And our ultimate goal is to figure out, well, could that then lead me to an equation that'll give me the amount present at any given time? And so that's what it means to solve a differential equation. It just means go figure out what the original equation was when you're given the derivative. And you might say, well, to go from the derivative back to the original, I just integrate. And that is part of it. It's a huge part of it. But before we integrate, we have to do something that's called separation. So we say that a diff-EQ, or a differential equation, is separable if you can write it as a product of a function and its differential equaling to like f of y dy equaling g of x dx. Written like that, it looks confusing, so let me throw one over here. Suppose we had dy dx, and suppose I had times x, and then over here I have y minus 1, like that. This isn't separated because I've got my differential with my x terms on one side, and then I've got my y stuff over on the right. So all we do is some manipulation. I want to solve for the top of this fraction, the dependent variable in the differential equation. So I need to get everything that has a y in it on the left, and everything that has an x in it over on the right. Or if it was like dw dt equals, I need everything with my w's over on the left, everything with my t's over on the right. To do that, I just manipulate. I divide by this to move it over. I'm going to multiply by dx to move it over, and then I'd have to divide by x to move it over. And now I've done what's called separating the variables. So, for example, this one is called separable because I could divide by 1 over root y to move it over to the left, and I could multiply by x to move it over to the right. And now it's in this format of f of y dy equaling g of x dx. And you'll see why that is incredibly helpful. If they are separable, then we can integrate, and so then we can eventually figure out what that y is. So here's what we call a method for finding the general solution to a differential equation. Right here I've got a differential equation. I have y changing over time, and if I were to read out what this means in terms of with words, I'd say the rate of change, the derivative of y, and then is proportional to y. It's actually 3 times y, so it's dependent on the amount present at the given time. Is kind of like money. You know, the amount of money that you have in the bank is proportional to the amount you put in, right? And it actually is dependent on the interest rate and stuff like that. This whole process gives birth to the PERT model that you used in Algebra 2. We'll talk about that later. So let's go do what we call separate. I'm going to put my goal is to solve for y. So I'm going to keep dy on the left. I'm going to move dt over to the right. All right, so we want to separate our differentials. Then I want everything with a y in it. I'm going to separate this. So I need to move this over. To do that, I do 1 over y dy. I actually could bring the 3 over also, but because my end goal is to solve for y, I'm going to keep all my constants sitting over on the right-hand side. I'm going to have to move them over anyway because I'm trying to isolate y. So I have 1 over y dy is equal to 3 dt. Now what I do is I integrate or take the antiderivative of the left-hand side and I set it equal to the antiderivative, or I integrate the right-hand side. And because of the variable match now, I can integrate. When it's not separated, you can't integrate when you don't have variable match. So the antiderivative of 1 over u du is ln, absolute value. So this would be ln, absolute value of y, equaling the antiderivative of a constant with respect to time would just be 3t. Now technically each one of these has a plus c on them, our arbitrary constant of integration. However, instead of putting a plus c on the left and a plus c2 over on the right, what we do is just lump them all into one big constant that would have been moved over to the right hand side. So only necessary to include one constant and it'll kind of absorb both of them. So my goal is to solve for y, and the inverse function of the natural log is to raise it e to that power. So both sides are going to go e to the, all right, e to the ln inverse operations just gives me absolute value of y. And over on the right, I have e to the 3t plus c. Now what I'm going to do with this is use an exponent property that when I have the same base, I add exponents, and I'm going to split that up. The reason is I'm trying to kind of suck all my constants out into one big constant. And e to the c is a constant. Some books will call it k. Some just call it c still, and that's what I'm going to do. But in order to legally drop the absolute values, a lot of people aren't picky, and I know College Board isn't very picky about when and how you drop the absolute value, but technically, I should really define that constant as plus or minus e to the c, because then I can absorb the absolute value into it as well. So I've got c e to the 3t. And I'm done. That's as good as I can get. It's called a general solution. Until somebody tells me a specific point on the curve, I can't figure out what that constant is. But we will be doing that eventually. So we're just going to go practice this process because it's actually, it's very concrete. So once you got it down, it's actually pretty easy. There's a few details to watch out for that we'll discuss, but other than that, it's just algebra. So our first thing is to separate then integrate. So I'm going to get, again, I'm trying to figure out an equation for y that's dependent upon x. And so I'm going to multiply both sides by y squared. I'll get y squared dy is equal to x plus sine x. I'm keeping all my x terms over on this side, over 3. And that would be times dx. It's now separated, so then we integrate. So you're going to integrate both sides of the equation. You're going to integrate the left side with respect to y, and you're going to integrate the right-hand side, and I think I'll just pull the 1/3 on out front since it is a constant, and I end up with that. So the antiderivative of y squared would be y cubed over 3. The antiderivative of x is x squared over 2. So I'm going to have 1/3, and then I'm going to have x squared over 2. And then I also have over here the antiderivative of sine. And again, one sign error, like S-I-G-N, will throw you off. So make sure you get that antiderivative of sine being negative cosine. So I'm at minus cosine x. And again, I have some constant that's hanging along as well. So right now, I could take the 3's off, just multiply both sides by 3. If I do that, I just get another bigger constant. So I've got y cubed is equal to x squared minus cosine x plus c. And then to solve for y, I get the cubed root. So I have the cubed root of x squared minus cosine x plus c. So let's go do the next one on here. And again, we separate and then we integrate. So I'm going to do 1 over y dy equaling x dx. Separated. Then I'm going to integrate. Antiderivative of 1 over y is ln y, absolute value. Be careful right here if you were to ever get like this, that you don't say that that's ln y squared. Remember, the natural log antiderivative is when it's in the form u prime over u, or 1 over u du, and this is a power rule problem. That's just y to the negative 2, which you would add 1. Remember, you use that power rule when your exponent is, we can't use it when it's a 1 because we would be doing, when you add 1, when you have y to the negative 1 and you add 1, you get y to the 0 over 0, which you can't do. So again, be careful how you use that. This is an ln rule on this side, but had that been a y squared or a y to the 4th, it would be a power rule problem. So we've got x squared over 2 for the antiderivative plus good old Carl. And then I need to undo ln. So I'm going to do e to the both sides of the equation. E to the ln is just the absolute value of y. They are inverse operations. We are going to write this as e to the x squared over 2 times e to the c. When we multiply, we can add our exponents, so those are equivalent expressions. I am then going to call this some other constant, and I'm going to actually define it as plus or minus e to the c. Not really necessary, but I have OCD, so I need to have that there. It's c e to the x squared over 2, and that's the best I can do until somebody tells me a point on the curve so that I can go find Carl, and that's what's up next. So in the next part, the title of this is called Who the Heck is Carl? We're going to have to figure out what that constant is. So again, we're going to start it the same way, but now they're telling me an exact t value that'll give me an x of 1. And remember, this is what I'm trying to solve for. This is what my equation is called. So if you get mixed up with the variables, t is going in, x is coming out. So let's begin. Let's separate. So I want to keep dx over here. I want to keep the x over here. I need to move the dt over to the other side. And I need to move that over, which means I technically, that as stands is 1 over e to the t. So I would multiply both sides by e to the t. Or you could think of dividing by e to the negative t, but then that also just gives you e to the t. So negatives go to the top when they're on the bottom. Anyway, now I'm going to integrate both sides. I'm going to integrate the right-hand side, find its antiderivative. I'm going to find the antiderivative on the left-hand side as well. So nothing new yet. X squared over 2 plus Carl, but he'll be lumped in on the other side. The antiderivative of e to the x dx is e to the x. The antiderivative of e to the t dt is e to the t. And now here is Carl. Now we're going to stop. You can technically find, and this is important, you can find the constant of integration anytime after you integrate. You can do it immediately, you can do it partway through, or you can wait till the end. It really doesn't matter, and that gets a little frustrating that you have that much freedom. But you really, if I want to go find Carl right now, I could. However, I'm going to choose not to, but let's suppose I did. Let's go ahead over here and write finding C now. If I were to find C now, what I would do is take 0, put it in for t, and take 1 and put it in for x. This is a point 0, 1, the point t, comma, x of t. So if I were to do that, I would go put a 1 in for x, and then over here, I'd get e to the 0 plus c. And I'd get 1/2 is equaling 1 plus c. And what that's going to do is give me c of a negative 1/2. And then I'd move along and continue. Well, I might as well do that since I started it. So then I'd go back to my original, and I'd say x squared over 2 has to equal e to the t minus 1/2. And what I would do right now is I would, remember my goal is to solve for x, so I double everything. So I would get x squared equaling 2e to the t minus 1. And then I'm going to get x equals plus or minus the square root of 2e to the t minus 1. Now it matters which one I choose, whether I choose plus or minus. And to decide, I go back and look at my original condition. Some books call that the initial condition. And what that means is basically you go back and let this point determine whether it's positive, negative. I know when I put in a 0, it has to poop out a positive 1. So when I put in a 0 for t right here, I get 2. And then 2 minus 1 is 1, and I need to have the positive root because it says 0, 1 is on that curve. So my answer is the positive root. Doesn't mean it's always positive, but it means for this particular differential equation, which with the initial condition of 0, 1, it will be positive. Now, on the left-hand side, all right, or right-hand side, sorry, I'm going to wait to find C. Suppose I just say, you know what? I'm just going to double everything right now. X squared is equal to e to the t, right, plus 2c, which is just some other constant. I could find it right now. I could say, all right, when t is 0, I know I need to get a 1 out. What that means is c is negative 1, and I'd get x squared is equal to e to the t minus 1. That's actually what I ended up getting over here, right? I'm just not done yet. Oops, I forgot to double that. Got to double everything. Anyway, I end up at the same spot. So when you find that C does not matter. I still notice it's a little smoother over here on the right, and that is a general rule of thumb. Get rid of fractions before you solve for C at least. And again, I get x is equal to plus or minus the square root of 2e to the t minus 1. When you work on these together, and then I choose the positive for the same reason I chose it over here. When you work with these together, it's kind of frustrating because you might be working with somebody and you say, what'd you get for C? And you'd say, well, I got negative 1/2. And then somebody else might say, well, I got negative 1. Well, that's because of where in the process you found it. So the moral of the story is you can find the constant of integration anytime after you integrate. All right, so one last one and we will quit. So let's go. Let's separate, integrate, find Carl. So the first thing I need to do is keep everything in terms of y over on the left-hand side. I'd have to multiply by y. I'm going to keep everything with my x over on the right, and I'd have to multiply by dx. It's now separated. I will integrate. The antiderivative of y with respect to y is y squared over 2. The antiderivative of 1 is x. The antiderivative of x is x squared over 2. And then I have a constant. I could technically go find the constant right now. However, I would wait. I would get the fractions out of there. I just double everything and you'll get y squared is equal to 2x plus x squared plus some other constant. 2 times a constant is still a constant. So you can just, if you want to write 2c, that's fine, but then you're going to get like if you got c, you would maybe get a 12, and if you did 2c, you'd get a 6, and then you'd plug it back in, you'd be right back at 12. So you can just go ahead and leave it as some bigger constant, doesn't matter. All right, so when do you want to find c? How about right now? I think it'd be kind of smooth. What I do is I put a 1 in for x, and I put in a negative 4 for y. So I could say negative 4 squared is equal to 2 times 1 plus 1 squared plus Carl. So I get 16 is equal to 2 plus 1 plus c, and I end up getting c equaling 13. So when I'm back at my original, right? Is that right? I think so. Yeah, looks good to me. So I like to indent when I find c, so I'm going to go back up here. I've got y squared equaling 2x plus x squared plus 13, which would mean y is going to be plus or minus the square root of 2x plus x squared plus 13. I have to now make the decision. Well, is it the pot? You can't have the function be two different functions. So it's either the positive or the negative. And again, I let that initial condition help me out. I want, when I put in a 1, which would be 2, plus 1, which is 3, plus 13, which is 16, I want to get a negative 4, according to the initial condition. It said up here that y of 1 is negative 4. So what that means is my answer is the negative square root of 2x plus x squared plus 13. This is called solving a differential equation by separation of variables. So the homework that goes with this section is the worksheet number 1. It's white. You'll do 1 through 12. 6 and 11 are bonus, and 12 gets done. Number 12 gets done in class. So have a good one.